second part of Chapter 5, Central Limit Theorem and its applications. First, let's consider the following two cases. The first case is where you have a random sample x1, x2 up to xn from a population which is normal with mean mu and variance sigma square. And then we denote the sample mean as xn bar. Then according to the sampling distribution of sample mean, we know that the expected value of xn bar or mean of the sample mean is the population mean mu and the variance of the sample mean is sigma square over n. And then we can say the sample mean follows the normal distribution with mean mu and variance sigma square over n. By standardizing, we can get xn bar minus mu over sigma over square root of n, which is the standard normal density, which is the normal distribution with mean mu and variance 1. Now let's look at the second scenario. What will happen if the population is different than the normal distribution? According to the weak law of large numbers, if we have a random sample x1, x2 up to xn from any distribution, no need to be the normal distribution, then the sample mean xn bar is close to the population mean mu in probability. But it does not mention about the distribution of xn bar. When it comes to the central limit theorem, it tells us about the distribution of the sample mean for any random variable when the sample size is large enough, or we may say sufficiently large. Then we have the question, what is the sufficiently large? What is that number? How large is large enough? First, let's look at the central limit theorem. It says that if x1 up to xn is a random sample of size n with mean mu and variance sigma square, then this quantity Zn, which is x bar minus mu over sigma over square root of n, is a standard normal distribution when n goes to infinity. So this is where the sufficiently large or large enough condition applies. Usually, if the sample size n is greater than or equal to 25, we say that it is large enough. And you can apply the central limit theorem. But it will depend on the distribution of the random sample. In another form, we can restate the central limit theorem as follows. You can say xn bar is approximately normal. So this is how you denote the approximately normal with mean mu and variance sigma square over n. Now let's look at an example. Now suppose you have a random sample of size 25. Okay, so this is exactly 25, so we can assume that this is large enough and you can apply the central limit theorem. It has the PDF given in the statement with the support x from 0 to 1. We want to find the probability that the sample mean of these 25 observations, that is x bar 25, is within 0.48 and 0.52 using the central limit theorem. Now we know that according to the central limit theorem, x25 bar, so that is the sample mean of this random sample of size 25 is approximately normal with mean mu and variance sigma square over n. So which means first we have to find the mean and the variance. Since the PDF is given, we can easily do that. So let's start finding the mean, which is the expectation of x. So you can find it by x times fx dx evaluated over the support of x. In our case, this is from 0 to 1, x times 6x 1 minus x dx. 6 is a constant, we take it out. So we end up with x square 1 minus x dx, which is 6 times x evaluated from 0 to 1, x square minus x to the 3 dx. Now let's evaluate this integration, which will give us the expected value of x or the mean. So that will be x to the 3 over 3 minus x to the power 4 over 4 evaluated from 0 to 1, and we will end up with the answer 6 times 1 over 3 minus 1 over 4, which is 1 over 2 or 0.5. Next, we have to find the variance. In order to do that, we have to find the second moment, Ex square. So we will follow the same method when x goes from 0 to 1. We have 6 outside. Now we have x square times 6 is already there. So x 1 minus x dx, which will end up with x going from 0 to 1, x to the 3, 1 minus x dx. Now we have x going from 0 to 1, x to the 3 minus x to the 4 dx, and by evaluating this we will have the answer 3 over 10. Now using the first moment and the second moment, we can find the variance or sigma square using the computational formula Ex square minus Ex whole thing squared. We already have these numbers. Ex square is 3 over 10, Ex is 1 over 2, and its square becomes 1 over 4, and the answer will be 1 over 20, which is 0.05. Now let's apply the central limit theorem. The sample mean is approximately normal with mean 0.5 and the variance sigma, which is 0.05 divided by n is 25. We want to find the probability, which is this x bar. The sample mean is within 0.48 and 0.52. Okay, now let's standardize this one. So we have x bar 25, subtract the mean, divide by the standard deviation. We do the same for the values. We know mean is 0.5, and then we have sigma over square root of n, which is 0.05 over 25 whole thing square root. And you do the same for the other side, 0.52 minus 0.5 divided by the standard deviation. If you have x bar minus mu over its standard deviation, you end up with the z value. And if you do these calculations, the left hand side you will have negative 0.44 and the other side you have plus 0.44. Now we can read the standard normal table for the area under the curve. It is symmetric about mean 0. We know the boundary now, which is from the z score negative 0.44 up to plus 0.44. So if you read the table, you will find that this probability is 0.34. So using the central limit theorem, you can find the required probability. Next, let's look at the corollary for the central limit theorem. Now suppose we have a sum of these random samples, x1, x2 up to xn, we add them together. So x1 plus x2 plus up to xn, we denote it as Tn, which is the sum of the random sample of this size n. And this random sample has the mean mu and the variance sigma square. Then you can say that the Tn, which is the sum, okay, that sum, if you subtract its mean, which is n times mu over square root of n times sigma, that is also approximately normal for using the central limit theorem. And this is also for sufficiently large n. So let's try to prove this one and see how we can get this approximately normal density for this expression. Here's the proof. We know that xn bar, which is x1 plus x2 all the way up to xn, that is the sum, and when you need the average or the sample mean, you have to divide this by n. So this is same as Tn over n. Now according to the central limit theorem, if you take xn bar, subtract the mean, divide by sigma of square root of n, which is the standard deviation, this is approximately normal 0, 1. This is for sufficiently large n. We can replace xn bar with Tn over n. So let's replace xn bar with, that is the sum divided by the sample size. Okay, the rest is same, which is approximately normal 0, 1. Still for sufficiently large n. Now let's multiply this expression by n. So we'll end up with just Tn, and when you multiply n by mu, you have n times mu. Okay, and then this n goes to the bottom, right? And that will give you n sigma over square root of n. For sufficiently large n. By simplifying the denominator, you will end up with Tn minus n mu. One square root will go away from the top, so you will end up with square root of n times sigma, which is approximately normal 0, 1 for sufficiently large n. So that is exactly what we wanted to prove. So here's another example related to that corollary. So you have a random sample of size 20 from a uniform distribution 0, 1. So T20 is x1, x2 up to x20. You want to find the probability that T20 is less than or equal to 12. So which means we need the probability T20 minus n mu square root of n times sigma less than or equal to 12 times 12 minus n mu over square root of n sigma. So that means we have to find the mean mu and the variance sigma first. It is given that this sample is from a uniform distribution within the interval 0 to 1. So therefore we know that the density of fx is 1 within the interval 0 up to 1 and 0 otherwise. From this PDF you can find the expected value and the variance. Ex will be integrating from 0 to 1 x times 1 dx or x dx, which will be x square over 2. From 0 to 1 we will have the expectation as 1 over 2. Then ex square will be 0 to 1 x square dx, which will be x to the 3 over 3 evaluate from 0 to 1, which is 1 over 3. From that you can calculate the variance of x, which will be the computational formula ex square minus ex whole thing squared 1 over 3 minus 1 over 4, which will be 1 over 12. Now we know the mean and the variance, so let's find the probability that the T20 minus n mu over square root of n, now that is the z value, that is less than or equal to 12 minus n is 20, and this mu we have found that it is 0.5, divide by square root of n is square root of 20, and then you have sigma, which will be the variance is 1 over 12, so the standard deviation will be square root of that value. And if you simplify this, you will end up with probability z less than or equal to 2 square root of 12 divided by square root of 20. And that will give you the number probability z score less than or equal to 1.5. Again, you can read the standard normal density curve. Z value is 1.55. You need the area to the left. Z less than 1.55. So if you read the table, you can find that this area is 0.9394. So that is the required probability. Now let's look at some applications of the central limit theorem. The first one is using the normal approximation to calculate binomial probability. You know by now that the binomial distribution is a discrete distribution. Binomial random variables are discrete random variables, but the normal distribution is a continuous type of random variable. But still, we can approximate the binomial probability using the normal distribution based on the central limit theorem. Now suppose you have x1 up to xn, a random sample from size n of a Bernoulli distribution with the success probability p. You know p is the success probability, it should be within the interval 0 to 1. So let's define x, which is the sum of xi, that is x1 plus x2 up to xn. That is the number of n independent Bernoulli trials. Then we can say x follows the binomial distribution with number of trials n and probability of success p, and we all know that the mean of a binomial random variable is n times p and the variance is n times p times q, or you can say n times p times 1 minus p. If you remember that corollary earlier, now our x is like the Tn, right? So you can write by central limit theorem x minus n mu divided by sigma square root of n, which is approximately normal 0, 1 for sufficiently large n. But we know that x follows the binomial distribution with the mean and the variance. We already know that. So let's apply it. The mean will be n times p, the mean of x, and its variance, which is n times p times 1 minus p, and the standard deviation will be the square root of that. So that will follow approximately a normal distribution from 0 to 1 for sufficiently large n. So which means you can approximate a binomial random variable x, which will be approximately normal with mean. What is the mean? Np, and the variance np 1 minus p. So that means if you know the mean and the variance of your binomial random variable, and if you have a sufficiently large sample size, in order to calculate the binomial probabilities, you do not have to use that binomial equation or the table. Rather, you can approximate it using the normal distribution. But the condition is you have to have sufficiently large sample size. Similar to the binomial distribution, you can approximate the Poisson distribution also using the normal density. Similarly, if you have x1 up to xn, a random sample of size n from a Poisson distribution, okay, so the mean parameter is lambda over n. Then let's define the sum x or Tn to be x1 plus x2 up to xn, that is the sum of the independent Poisson random variables. Then x will have, x is the sum of these xi's, then x will have the Poisson distribution with parameter lambda, because you have lambda over n times. So when you multiply lambda n times n will cancel out. So the summation will have Poisson density with the parameter lambda. Then by the central limit theorem, again we apply the previous corollary. So you have xn bar minus mu sigma over square root of n, which is approximately normal 0, 1 for sufficiently large n. And xn bar is what? That is x over n. X is the sum of x's. minus, and its mean. Now this is about x's, okay, not the sum of x's, just xi's. They are sigma over lambda over n, and the variance lambda over n square root divided by square root of n is approximately normal 0, 1 for sufficiently large n. This is because we know that when xi's are Poisson distribution, the expected value of each of these xi will be lambda over n, and the variance of these xi's will be still lambda over n. Okay, so for Poisson density, the mean and the variance both are same. Okay, therefore from that we will end up with x over n, which is x bar, minus lambda over n divided by its standard deviation, which is approximately normal. And if you multiply everything by n, you will simply end up with x minus lambda over square root of lambda is approximately normal 0, 1 for sufficiently large n, which means our random variable x will follow approximately normal distribution with mean lambda, variance also lambda for sufficiently large n. So that means the Poisson distribution, also the calculations of the probabilities, you can use the normal density, again only for sufficiently large n. Now as a rule of thumb, when you do these approximations, for Poisson, when n is large, so that will indicate that lambda is also large. Okay. Now let's look at some examples where you can approximate the binomial density and the Poisson density. Now before we do that, we have to look at something called the normality correction or the continuity correction. The reason is both binomial and Poisson densities are discrete type of distributions, but normal distribution is a continuous distribution. Therefore, when you are approximating a discrete density using a continuous density, you have to apply a continuity correction. Now this is how we do that. Suppose your required probabilities are as follows. These are the required probabilities, and this is how you apply the continuity correction. So you have to make sure you apply this continuity correction whenever you use the normal approximation to either binomial or Poisson distribution. Now the first one is, if you want to find the probability x equals a. Now remember, when you have discrete distributions, the point probability is possible. But when it comes to continuous distributions, the point probability is 0. If you are approximating a binomial probability, binomial is discrete, so it is possible to find this probability x equals a. But if you are approximating it with the normal density, the point probability is 0. So such situations, you do this continuity correction, you find the probability by adding and subtracting 0.5 to the value a. So the probability x equals a is same as, or after the continuity correction, that will be the probability x is within the interval a minus 0.5, a plus 0.5. And then if you want to find probability x less than or equal to a, then the continuity correction, you do x less than a plus 0.5. You add 0.5. If you need only x less than a, again remember, since the point probability has a value, x less than a and less than or equal to a are two different probabilities in discrete case. But when it comes to continuous case, x greater than or equal or just greater than, both are same. Now when you are using the normal approximation to binomial, you have to be careful. When you have x less than a, the continuity correction will be x less than a minus 0.5. Similarly, you can do the greater than a. In that case, it will be x greater than a plus 0.5, and then x greater than or equal to a will be probability x greater than a minus 0.5. So this continuity correction, you have to make sure to apply it when you do calculations. Okay, so here's our first example, the binomial approximation. Consider the independent single baby births in which the probability of a boy or a girl is each assumed to be equally likely. So when you see equally likely, that means it is 50%, 50%, or 1 over 2, 1 over 2, 0.5, 0.5. Equally likely. So that means the total probability 1 is equally divided among the two cases, boys or girls. Let x be the number of boys. Now our success event is defined as the number of boys. Now suppose you randomly choose 1000 baby births. You want to find the probability that strictly more than 470 of the babies are boys. So what is that? Probability x greater than 470, strictly more than, that means no equal sign. Okay. So how do we do that? If this is the binomial density, when x follows the binomial density, what is the number of trials? You are choosing 1000. So that is large enough. And p is 0.5, that is the probability of success. Probability of being a boy is 0.5. Now you know n and p, therefore you can find the mean and the variance. Okay, so let's first find the mean mu, which is n times p, 1000 times 0.5, which will be 500. And the variance, or sigma square, is n times p times 1 minus p, which is 1000, 0.5, 1 minus 0.5 is also 0.5, so you have 250. According to the central limit theorem, x will follow approximately a normal distribution. What is the mean? Mean will be 500 and the variance is 250. Okay, so we want to find the probability x greater than 470. Right, so this is approximately probability x greater than 470 plus 0.5. Okay, that is from the continuity correction. See the fourth one. Okay, so that will be probability x greater than 470.5. Now we are going to standardize this one, which is x minus mu over the standard deviation. So that will be 470.5 minus 500 divided by 200 square root of 250. So that will be z greater than negative 1.8657. If you do the calculation, you will end up with z greater than negative 1.8657. Then you can read the z table. Yes, negative 1.8, you can round it, 1.86. Okay, and you can read the table, the left tail, and then by symmetry it will be same as, this is same as probability z less than positive 1.86. You can find the probability and that will be 0.9693. In the same question, the next is find the probability that exactly 500 of the babies are boys. Exactly. So that means probability x equals 500. Now you have to add the continuity correction. That will be 500 minus 0.5 and 500 plus 0.5. So that will be the probability 499.5 x 500.5. Okay, so we'll approximate this with the z-score, subtract the mean, divide by the standard deviation, which will be the z-score. Do the same for the other side, subtract the mean, divide by the standard deviation. So that will be probability negative 0.0316. Again, you can read the standard normal table. Now this is by the symmetry, you can easily do that. This in between probability negative 0.03, positive 0.03. Okay, you can find this middle probability and you will see that it is going to be 0.0240. Now let's look at a Poisson random variable, an example on how to apply the central limit theorem. A publisher estimated that each 500-page book has a Poisson number of typos with lambda 100. So there are 100 typographical errors per 500-page book. You have to find the probability that there are strictly more than 80 typos. Okay, so what is lambda here? Lambda is 100. Lambda is 100 and that means the mean is also 100 and variance is also 100. We want to find strictly more than 80. So x greater than 80. Again we apply the central limit theorem, subtract the mean, divide by the standard deviation. Our x becomes z. Which is the continuity correction first. What is it? Greater than 80 is 80.5. Right. So you have 80.5 minus 100 over square root of 100, because when lambda is 100, mean and variance both are 100 for the Poisson distribution. So if you do that, you will end up with probability z greater than negative 1.95. Again, you can read the standard normal table. Yes, the negative 1.95 greater than that. Okay, so that is same as probability z less than positive 1.95. And if you read the table for that, it will be 0.9744. So that is how you apply the central limit theorem and use it when you have to approximate binomial probabilities and Poisson probabilities. Before we wind up the examples, there are a few conditions that you have to satisfy when you do the approximations. You can do these approximations when n is sufficiently large, and also for the binomial situation, make sure to check also that is n times p and n times 1 minus p both are greater than 5. Both of them should be greater than 5. Okay, so you have to check this condition also before you proceed with the normal approximation. Okay, as a rule of thumb, both n times p and n times 1 minus p should be greater than 5. Okay. When n is very large, usually this will be satisfied, but it is always good to check whether np is greater than 5 and n times 1 minus p is also greater than 5 for the binomial situation.